Thank you. And we are now recording.
All right, sounds good. Thank you all for coming to our final product presentation. We are Zebra Team 6, consisting of the following team members.
I'm Hugh Brittenham.
I'm Alexander Davis.
I'm Eric Lee.
I'm Sarah Moran.
I'm Ami Patel.
I'm Brett Winter.
And I am Alexander Hadid. Covered in this presentation consists of the overview of our design and development of our product. Following will describe and show the specifications that our product addresses, along with CAD models created using SOLIDWORKS CAD software, with a further breakdown of the cost to make a prototype and 100-unit production run. Testing and further development will also be presented for the near future of the product. The design overview will show how we came to our hedgehog concept, how our variability in the proposed product adheres to the customer needs, and a breakdown of our assembly with the relative analysis done to complete the design. With our hedgehog concept, we came together to decide what we were all best and passionate about. The first idea that came to us was our proficiency in solid modeling or computer-aided graphics and design, along with a passion for animal safety. From our proficiency with CAD, we branched out and found that our drawing capabilities and knowledge with manufacturing are all areas that we are proficient in, as well that have aided in our knowledge of optimizing the designs. Another common theme in our group was our passion with brain and disease research that goes along with animal safety. Since we share 70% of our genome with zebrafish, selective plane illumination microscopy measures the effects of different therapies and drugs on the neural and behavioral activity of the zebrafish. When it comes to the economics, we sought to create a design that is cost efficient in minimizing off-the-shelf parts and material cost, while also maximizing the profits to be gained. This led to an overall theme of optimization during our design that refers to manufacturing cost, accessibility, the time to assemble and disassemble the product, and how easy it is to use the product. With the variability in our proposed design, our team sought to create a product that is an affordable and easily accessible system of optical accessories that can be used anywhere with mass-producing methods of 3D printing or injection molding compared to more labor-intensive methods. Following these terms for our product, we have created a design that has adhered to the needs outlined by the customer, that the imaging chamber and zebrafish holder both need to be optically transparent for the laser to accurately record the zebrafish's behavior under different stimulations and define functional measurements. The need for the laser to have easy access to the zebrafish through the imaging chamber is also achieved by the materials and manufacturing methods that will be presented later. Although our focus is to adhere to the needs stated by the customer, the first need we address with our design is to ensure the safety of the zebrafish specimen itself. And this was completed by having all products designed to keep not only the specimen safe, but also the user safe as well when handling the components. Our products also have been designed to be unique in the sense that in the future, the products will also be used and still in the market, while also being compatible with already existing products. Our group decided that our final product design has met and fulfilled the needs from the customer, along with taking the selected mounts by the customer and improving upon the design, which resulted in being the main focus of our design. The first and second objective sought to create an optical imaging chamber and zebrafish specimen holder that adheres to the customer's specified dimensions, opacity, and safety levels. The third objective was to replace the off-the-shelf mounts with magnetic mounts that prevent deviation from the nominal orientations and provide continuous modularity in terms of the fixturing on the optics table and in the Z direction. The final objective we sought to complete with this design is to ensure that multiple optogenetic experiments can be completed with an optical alignment for the optogenetic stimulation laser path that accounts for the customer's specified laser parameters and minimizes aberration.
So now I'm going to go into kind of the scale of the overall system design. The entire assembly setup, including the laser path, mounts, imaging chamber, fish holder, and path switching subsystem, fits to a standard 18 by 24 inch optical table. The imaging chamber's dimensions were directly specified in the customer needs statement as 76.2 by 76.2 by 38.1 millimeters. Additionally, the customer needs directly specified the dimensions of the platform holding the zebrafish suspended in agarose gel as 38.1 by 12.7 millimeters. The mounts that our team designed have a base that takes up roughly 76.2 by 63.5 millimeters on the open lab table. To scale, one side of the entire microscopy setup is 305 times larger than the 5 to 7 day old specimen in which the setup is built to analyze. Next is a subsystem breakdown. On the far left, you can see the imaging chamber and fish holder composed of acrylic. In the middle is the path switching subsystem, and to the right is an example of our mounting solution. When going through the process of quantifying the customer needs, the team grouped together the needs into separate groups characteristic of the design aspect they were addressing. Through this, we were able to identify these 4 subsystems. First, the fish holder was designed to satisfy the need to not only hold a zebrafish in the tank, but to also keep the zebrafish secure and unharmed through changes in elevation and acted by a Z actuator in which the fish holder is mounted. The imaging chamber was identified as the subsystem responsible for not only keeping the zebrafish surrounded by water, but for also allowing accessibility both laterally and from the top of the chamber for laser entry and light projection. The imaging chamber is equipped with an Arduino pH sensor, able to provide accurate pH readings to determine when the water is out of the required 6.8 to 7.5 range. The wall containing the glass viewing window of the chamber is able to be removed from the body of the tank to allow the customer better access for sterilization. Both subsystems were designed to be optically transparent as specified by the customer. The path switching subsystem redirects the 438 nanometer laser in between the light sheet and optogenetic stimulation paths while causing no crosstalk between lasers. The path switching subsystem comes equipped with a 3D printed hinge adhered to the side of the customer specified magnetic mirror mount. The magnetic mirror mount is able to be pried off of its bottom plate using a ball end screwdriver to change the desired path. The mounting subsystem is designed to house the required lens and mirror components required to complete the laser beam dimensional manipulation before hitting the zebrafish. The mounts come equipped with magnets embedded within their base, allowing them to be easily placed and removed from the magnetic optics table. The mounts are able to magnetize to the table through the use of a sheet metal attachment that covers the top surface of the optics table breadboard. The sheet metal cover comes equipped with hash marks denoting each 1/8 inch measurement along all sides of the optics table. The hash marks allow users to be able to place the magnetic mounts at exact distances required for experimentation. The mounts have continuously adjustable height through a track and set screw system, providing the user full customizability of their experimentation setup. Despite the imaging chamber not even being large enough to hold an entire cup of water, the team took its due diligence with assuring the tank would be successful in fulfilling the customer's needs. The imaging chamber's material was found utilizing an Ashby plot analysis. The customer's requirement for the imaging chamber to be optically transparent narrowed down possible selection significantly, with acrylic providing the highest durability for the lowest cost. We calculated maximum pressure constraints and acted on the tank walls by the water and determined that the maximum possible stress enacted in this manner comes nowhere close to the yield strength of the acrylic material, providing an exorbitantly high factor of safety. Aside from the pressure, the total load due to the weight of water against the bottom mounts was also taken into consideration and proved to maintain a factor of safety higher than 100. From this point, it seemed that the chamber was more than qualified to perform the typical duties highlighted in the customer needs. Despite this, the team wanted to take into consideration the possible jarring movements that could occur to the imaging chamber. The team knew that the imaging chamber was designed to be repeatedly sterilized, and it was bound to be knocked into a counter or possibly dropped. Using material property data, the team used the laws of conservation of energy to determine both the minimum drop height required to fracture the acrylic, as well as the minimum impact velocity. The imaging chamber would have to be dropped from a height of over 9 meters to fracture the acrylic, which was deemed highly unlikely when considering the chamber's use and environment. It was determined that the maximum impact velocity that could fracture the acrylic material would be over 13 meters per second, which is once again well within the constraints of a working laboratory. The fish holders material was also found utilizing an Ashby plot analysis. The customer's requirement for optical transparency, once again, narrowed down all the possible selections, with acrylic being the most durable for the lowest cost. The weight of the zebrafish placed upon the fish holder was found to only be 71.6 milligrams, providing no serious force cantering the fish holder downward. But once again, the team wanted to take into consideration the fact that the fish holder will be detached and sterilized throughout its lifetime. So the team used the laws of conservation of energy to once again determine the maximum drop height and the maximum impact velocity, which was 9 meters and 13 meters per second, which is once again well within the constraints of a working laboratory.
For the optic mount, the material was selected using an Ashby plot analysis. We utilized a clipping system, which became the main requirement for narrowing down our material selection. After analysis, it was found that a polypropylene copolymer proved to be the most optimal material based upon the durability and its low cost. The average weight of the optics components is extremely low, about 100 grams, providing no serious force cantering the mounts downward. Once again, the team wanted to take into consideration that the mounts will be detached from the breadboard often for sterilization or for movement, so further analysis was performed to determine the constraints of our plastic material. In the same way done to the imaging chamber and fish holder, the team used the laws of conservation of energy to determine both the minimum drop height required to fracture the material, as well as the minimum impact velocity if any mounts were to be swung and knocked over. The mounts would have to be dropped from a height of over 7 meters to fracture the plastic, which was deemed highly unlikely, and would require an impact velocity of 11.35 meters per second, which once again was within the constraints of a laboratory. Additional analysis was done to ensure the stability of the mounts once placed upon the board, so a static analysis was completed on the magnetic fasteners, and it was found that we had over 10 pounds of force holding the magnetic mounts to the board, as well as over 8 pounds of force to resist any transitional movement that occurs if the mounts were nudged during placement or manipulation of other components. When selecting the material for the path switching device, it was necessary that they can withstand wear caused from being repeatedly pried open using the ball driver. However, epoxies were eliminated due to being slippery when wet, and this can cause issues with accurate positioning as water will be in proximity. Carbon steel was eliminated due to the higher cost compared to the rest of the materials, and the weight of the subsystem would be much greater in comparison to the other materials as well. Polypropylene has poor bonding properties as well, which may cause problems when applying the adhesive to attach the hinge. Thus, ABS plastic was the best choice given the availability of 3D printing services at the University of Florida, as well as the material's low cost and durability. With the chosen concept for the path switching subsystem and the material set to be ABS plastic, further analysis was needed to determine how much torque is needed from the ball driver to determine how well the adhesive will hold via a shear stress calculation between the hinge and optical components. Finding a factor of safety in designing for a long life cycle is important to this analysis. On the adhesive website, the strength of the Loctite clear silicon waterproof sealant is 220 psi when properly applied and fully cured on the component. It was found that the maximum torque applied to the system is 97.2 psi. Typical factors of safety when regarding shear stresses is between values of 1.5 and 2. Since this design has a factor of safety of 2.27, it can be concluded that this design is both safe and reliable for long-term use.
The product development section will show you guys how we came to our current design concepts and how these concepts were realized based upon analyses carried out shown in previous slides. For the imaging chamber, the process of product development involved us making multiple concepts for each subsystem, choosing the best ones and compiling them into the finished product. And the concepts themselves also went through different evolutions. Using the imaging chamber to start off with, it started as a singular hollowed out piece of acrylic and developed into using acrylic wall panels with a removable window panel. The removable wall allows for easy assembly, disassembly, is released. And additional details were added as time went on, such as a pH and temperature sensor, and that's to ensure the safety of the zebrafish. The fish holder was one of the more straightforward parts of the design, but it still went through a few changes. The first iteration was a simple Z-shaped holder that was connected to the specimen via adhesive. However, given the unreliability of adhesive on its own, we decided to use an interference fit that will provide additional stability to keep the specimen in concerns regarding adhesive and the agarose gel. On the top portion of the fish holder is two fastening mounts that secure to the Z actuator. And we chose to put the mounts on the top of the actuator to allow for easy fastener removal without the imaging chamber getting in the way. The optics mounting designs were made to have a balance between being secure and allowing for free movement. Initially being fixed in place with discrete positioning of the Z-axis, subsequent iterations allowed for more precise, continuous movements. Rotation was also addressed so that small changes to the mount angle could be made in place. Additionally, the mount must be securely attached to the base as to not allow for any changes in angle. And this was done by adding the magnetic clamping system between the breadboard and the mounts. The simple task of separating the top and bottom plates of the kinetic mount was also taken through a few different concepts, from actuators to the rotating bases of recliners. The agreed upon design uses a hinge to connect the two plates and ensure that they're both aligned. Initially, the hinge was secured to the mount via screw fasteners, but the path of the plates makes for a relatively low shear stress on the face of the hinge, so we decided that adhesive would be sufficient. As for the material, it was determined that 3D printing the hinge would provide enough structural stability and it would remain low cost.
The product specification and CAD, this section will kind of explain what the major components of the system are and the functioning of the CAD models. Now, the major mechanical parts that comprise the subsystem are as follows. It's the outer optical mount sleeve, the inner optical mount sleeve, the sheet metal table cover, the imaging chamber body, the imaging chamber viewing window, the fish holder body, path switching magnetic base, the path switching bracket, and the ball head screwdriver. These mechanical parts can be organized into three different systems: mounting, imaging chamber, and path switching. The mounting system, which is the bottom left picture, is comprised of the optical mount sleeve, the sheet metal is comprised of the optical, inner and outer sleeves, and the sheet metal table cover, and it is what holds the optical elements in place. The imaging chamber system in the bottom right provides safe housing for the zebrafish and is comprised of the imaging chamber body, the viewing window, and the fish holder body. Lastly, the path switching system enables 488 nanometer laser to be directed into either the optogenetic stimulation path or the light sheet path. The path switching is comprised of the magnetic base, bracket, and ball head screwdriver. Now, this is our mock setup for our optical system. Currently shown here are 6 of our magnetic mounts and the magnetic attachment for the breadboard that ensures attraction between the mounts and the board. Now, this illustrates the layout of the system and all the mounts positioning relative to one another. Elements such as the periscope, the DMD, shutter, and OD wheel are provided by the customer and are shown in here to be integrated into the system design along with our mounts. Now, this path deviates from the customer specified one. Now, this is because we compromise with the customer to help design new mounts that reduces costs and preserves optical precision. Now, this is a fully developed optics path, which includes our mounts and the lenses, mirrors, imaging objectives, and beam expanders to kind of show you how the 488 nanometer laser will travel along the path and will ultimately be guided to the zebrafish sample in the imaging chamber itself. Now, looking at the CAD model, on the left, we have the imaging chamber with the fish holder. Now, this subassembly features press fits that enable easy installation and uninstallation. Now, the viewing glass window is press fit into the removable wall, which is then press fit in the imaging chamber body to produce a sealed container. The imaging chamber body has slits all along the height where the removable wall interfaces to ensure that the window isn't askew after installation. Additionally, the fish holder is then attached to the Z actuator, which isn't shown in the picture, and is placed in the center of the imaging chamber cavity. On the right, we have the magnetic mount subsystem, and this is comprised of 4 different components, which enable continuous movement in the Z direction and prevents rotations about the Z axis. Now, there are 2 cylindrical components shown in the first picture on the right magnetic mount, and they are concentric with one another, and they slide along the tracks to ensure that you can set it to the desired height. The set screw is then used to fasten that outer cylinder to prevent the height from altering. Additionally, the magnets embedded in the base of the mount enable easy mounting to the sheet metal optics table and easy adjustments and alterations to acquire the desired orientation of the optical elements.
This cost breakdown will outline the total cost to develop a prototype and a 100-unit production run of our design. To develop a prototype of our design, the customer has provided us with a $450 budget. The material cost for the imaging chamber and fish holder sums to $180.87. Using the University of Florida Fabrication Lab's laser cutting service for 67 cents per minute to cut the acrylic material and the glass viewing window, the manufacturing cost totals to $20.10. So the total cost of these 2 subsystems is $200.97. The total cost for the path switching subsystem is $11.26. Purchased parts for this subsystem include a 3D printed ADS plastic hinge, which would be printed for free through the University of Florida, and a ball end screwdriver purchased online. Furthermore, the watertight adhesive used in the imaging chamber can be reused here to adhere the hinge to the magnetic base. The material cost for the mounting subsystem is $207.16. This cost includes embedded magnets, the tabletop sheet metal, and set screws. The polypropylene copolymer mounting components can be 3D printed for free through UF for this prototype. Again, utilizing the UF Fabrication Lab, laser cutting the sheet metal tabletop would cost $13.40. So the total cost for this subsystem is $220.56. Overall, the total cost for a prototype design sums to $432.79, which is under our budget of $450. Now for a 100-unit production run of our design, the customer has again given us a budget of $450 per unit. The total material cost for 100 units of the imaging chamber and fish holder subsystem is $10,637.68. Again, utilizing the UF Fab Labs laser cutting service, manufacturing these parts will cost $2,010. So the unit cost for this subsystem is $126.48. The total material cost for 100 units of the path switching subsystem is $1,126. Additionally, 3D printing the hinges through Xometry, a manufacturing company with locations near Gainesville, costs $250. So the unit cost for this subsystem is $13.76. For the mounting subsystem, the total material cost is $15,227.75. Additionally, 3D printing the mounts through Xometry again costs $5,050. Using UF Fab Labs laser cutting service, cutting the sheet metal tabletops will cost $1,340. This totals to a unit cost of $202.78 for this subsystem. So overall, the cost per unit for a 100-unit production run is $343.02, which is under our budget of $450. Assembly of this design will be completed by our team ourselves to avoid extra labor costs. For this design, all that requires assembly is adhering the hinge to the magnetic base and assembling the mounts. This design aims to be versatile and allow users to position the mounts wherever they desire. So when this product is shipped to buyers, the mounts will not be prearranged on the optical board. Rather, they will be sent disassembled so that the users can position them wherever they desire for whatever optical setup they're trying to complete. A single kinematic mirror mount from Thor Labs costs $115.27. Our mounting system provides 6 mirror mounts as well as the tabletop for only $200.78. This justifies our team's decision to pursue a different route and redesign the mounting system. Additionally, 3D printing was chosen as a manufacturing method over injection molding because for 100 units, 3D printing these mounts is cheaper than the upfront cost for injection molding. However, for a larger scale production, injection molding could be used as a manufacturing method.
Future testing and development will specify why our team should be chosen and what our plans will be if our team is chosen. So our team provides many unique and optimized ideas that differentiates us from our competitors. Through the use of magnetic mounting, the positions of the mirrors can be customized to match multiple desired pathways rather than being locked into a single pathway, and have variable heights that reduce the need for additional components when aligning light microscopy experiments. The cost of our lab microscopy setup is significantly lower as well, due to the fact that we are creating our own optics mounts rather than buying them from outside sources. Additionally, our design team has shown that we are capable of adapting to new constraints or changes in customer direction while finding solutions that diverge from what may be considered conventional. It is this approach that we have brought to this project, and it is this approach we will continue to bring to any future projects. If selected, these are the proposed steps to improve our current ideation. In lab testing of prototype models, we'll provide additional research and proof of our material selection and current thickness for our plastic components. This would show whether or not we over-designed our components, in which case we reduce the amount of material we're having and lower production costs. Additionally, if our stress values prove to underestimate the real forces, we'll return to concept generation and/or material down selection, depending on the degree and the style of failure. The true value of our design is our improvements made to off-the-shelf parts. So a true comparison of failure stress, weight difference, setup time, and ease of setup will need to be conducted using various degrees of expertise from users. When we prove successful, the next step is to begin replacing more and more Thor Labs mounting apparatus, beginning with the discrete adjustments of lens angles from the lens holders. This will either take the form of an additional component to add to our pre-existing mount or a new assembly altogether. Finally, as production begins to develop and demand increases, we shall look towards different ways to produce our components that are now feasible due to demand. In conclusion, Zebra Team 6 seeks to create an affordable, accessible, and modular system of optic accessories that can be utilized by labs across the country. We've gone through various concepts and are proud to present these subsystems. An imaging chamber that features a detachable viewing window and pH sensor for proper laser light protections and specimen comfort. A fish holder that can easily be removed and have the agarose gel applied and hold the zebrafish in a safe and secure manner. Our mounting system that highlights the practicalities of magnets in manipulating stationary objects' positions, as well as our track system that adjusts the height of our mounts in the range of a few millimeters to a few inches. Finally, our path switching device operates on a binary system of following either an optogenetic path or a light imaging path. And as always, it will be the customer's role to properly use, position, sterilize, apply, switch, and remove all components, as well as provide parts that will be needed to complete experiments in the lab. Thank you to all the sponsors, customers, and people that joined us today for our presentation. Are there any questions?
All right. Any questions from our panelists?
Yeah, so this is Rick Miles from Northrop Grumman. So you mentioned early on in your presentation that you were going to have a pH and temperature sensor to make sure that the fish was okay. What are your limits there? And it just seems like this is going to, what I'm still trying in all these presentations, I'm still trying to picture how long is this fish within this box going through this process. Really, are we going to heat up or really be concerned that much with the pH and the temperature of what's containing that zebrafish?
Numerous experiments have been done, and some of our research went into the potential heating of the zebrafish. Typically, these experiments last for about 500 milliseconds, but in experiments when they were heating up, in research, it was rat brain tissue. Leaving the laser focused on for several minutes at a time, it increased the temperature only by 2 degrees Celsius. So while it is not a necessary concern in terms of temperature, there is always the potential for erroneous things to happen in a laboratory setting. So we always want to make sure that our specimen are in a safe environment.
Okay, I guess my thing there is whether or not it's something that the customer wants to pay for, right? You only want to give the customer what they really want. And so I guess I would be curious whether or not the customer wants that level of fidelity. Because if they, I agree, if you're going to say have a control environment, as a scientist, you probably want to know that data, but I just confirm with your customer that that's something that they wanted. The other thing you talked about early on is you started out with the idea of a hollowed out acrylic and then moved to having panels of acrylic. Walk me through that thought process.
Having just a hollowed out piece of acrylic, it seemed like the best manufacturing method to go about something like that would probably be injection molding. And for only 100 unit production run, it didn't seem very viable to pursue that sort of design. So trying to go with the sheets of acrylic instead, we could go about adhering them together with some waterproof adhesives and doing simple cutting to be able to construct that, rather than having to go down the whole injection molding route.
I do appreciate you actually headed off at the pass one of my questions, the additive manufacturing versus the injection molding question, right? By talking about the small quantity of 100 additive still going to be cheaper. Then later in your presentation, you mentioned fatigue analysis. What would you be running a fatigue analysis on in the future?
I think one of the big things would be insertion and pretty much taking in and out the viewing window of the imaging chamber. That's an interference fit, and anytime you're having those parts sliding against each other through several 100 to 1,000 experimentation cycles, there could always be some kind of failure that comes about from those two materials interacting with one another. Similarly, some kind of fatigue with the 3D printed hinge of the path switching subsystem. When you're moving it back and forth, you can only expect that over a period of time, there's going to be some kind of fatigue or possibly some kind of failure that could come up. So we were really interested in, if we're moving on to that next prototyping process, going about the proper testing that could kind of verify and validate our design decisions.
Okay, so along those lines, could you go back to where you were analyzing the loads?
Yes, so that'll be like slide 9, Alex.
Yeah, I got it.
And also, since you had brought it up, kind of backtracking a bit, it was one of the customer requirements to ensure a environmentally regulated for temperature and pH and chemical.
Okay. So I see this imaging chamber analysis. Do you have something on the fish holder itself?
For the fish
Next
holder
slide.
stuff, we did the kind of impact velocity and height. We felt as if that was probably the most likely mode of failure that could occur to that piece, especially because it's so small to hold in your hand when you're trying to sterilize it. That's also kind of why we tried to go with a singular continuous piece of material for that as well.
So I would expect most likely what your max loads are that you're going to have to deal with is going to be handling loads. So you just want to investigate, typical handling loads that you deal with this sort of structure. It's probably just a few pounds or something, but that's what I would expect to be your driver from an analysis standpoint, is what sort of handling loads you'd expect to experience with this particular structure. So. And then I guess this still is just the thing that I struggle with on this. So I appreciated you going through the optical analysis and stuff like that, but I'd still really like to have a good solid cartoon that really explains to me what you're doing with this particular design. I just even if I don't know, it's hard for me to. I'm still conceptualizing after all these presentations, how are we pointing the laser at the fish, right? And so I'd just like to have some sort of cartoon or whatever that kind of demonstrates that in the presentation up front to get that across to the customer or whoever you're presenting to. That's all I've got. I'll let everybody else ask questions.
Thank you.
So
I'll
I
go
have a
ahead and,
question.
oh, go ahead.
Sorry. So did you consider the human factors aspect of all the interference fits, how the user is going to interact with all of the tools?
I do not think that we had in-depth analysis of tooling for the actual putting together of all the interference fit parts.
All right, I have some questions and some comments. Fred Pendon from Carrier here. So I really like the fact that you led off with the customer needs. That's something that sometimes gets lost in these things and sort of should be at the center of everything you do. And I think it's come up. I mean, I think Rick was touching on that too, what the customer actually was asking for. So I think that's important, and I'm really glad that you had slides dedicated to that. So well done. Same thing with objectives, which is of course sort of a trickle down of the customer needs, but still important that you mentioned all that. So and that's something that we do all the time in product development out in the industry. So it's kind of nice to see that you guys are catching on to that already, because it's something you're gonna sort of live and breathe as you get out into the world anyway. So good work there. I did write down the whole pH sensor requirement, but I think it's been answered. So well done there. So the one thing that I don't think we've talked about is that whole screwdriver thing. I was a little confused as to how that works, or if there's a dedicated screwdriver for every. It's the redirect hinge thing. Can you explain that a little further, please?
So the part that the customer specified would be used for the first mirror in this optical arrangement is a magnetic mount, which basically consists of two plates that are magnetized to each other. And in our subsystem, we have that part, which is customer specified, as well as the mirror, which again is customer specified. And through researching this part in general, we found that Thor Labs recommends separating the two magnetic plates from each other using a 532 ball end screwdriver. So to sort of represent how these plates could be pried apart, we included this ball end screwdriver in our CAD models. Essentially, the screwdriver is just used to pry the plates apart, and there's a laser that would come towards this mirror. And when the plates are pried apart, the laser could shoot straight past the subsystem in general and just move on to the next mirror in the orientation. But when the plates are together, the laser will bounce off of the mirror and follow down another path.
Okay, so it's basically they have one of these on hand just in order for that operation then.
Yes.
Okay, thank you. Well done.
You're welcome. Thank you.
Okay, any other questions or comments from our panel? I see Julia's unmuted there.
Yep, I will be fairly quick. Can you go back to your cost slides, please?
Yes, I can.
Okay.
1 minute.
Okay, so I will admit I was slightly confused when you were going through all these. A lot of information. So maybe figure out a way to more simplify this. So I understand for the prototyping, it's not going to include any assembly costs because y'all are doing it yourselves. Not a problem, right? So go to the next one, go to mass production. There we go. So correct me if I'm wrong, but I think I heard you say that you as a team would be assembling these yourselves, or I think I may have misheard this.
That is correct.
Okay. Are you going to pay yourselves? Because if you're not going to pay yourselves for work, like I've got a lot of housework to do over here. Like, please come to my house. So believe me, I totally understand the idea that you want to save money by doing it yourselves, but you got to remember too, you guys got to eat, you know, you got to survive, you got to live, you have to pay yourselves. You know, if you're going to work for free, I guarantee you everybody out here will find some work for you. So in labor does eventually get very expensive. Okay. So you're probably not going to want to be the person that's constantly assembling these for, you know, days on end. Yeah, it looks like Dr. Trum needs help cleaning the lab. Again, if you're working for free. So you're definitely going to want to go back and reconsider your costs and put in labor costs there, because that gets quite expensive quite quickly. Okay. The other thing I think I heard you say, now granted, I'm not familiar with what the fab lab or something like that, the fabrication lab there at UF. So they charge you what, I think you said like 30 cents a minute or something along those lines. Are you able to use that lab when you are no longer students?
Yes, it's a public use lab.
It's a public lab. Okay. Again, I know nothing about the Fab Lab, so I just love the name, so I'm going to keep saying it pretty much.
But also, since you had brought up the production costs, we did a rough time analysis, and it takes 209 seconds to assemble all of our mounts, which boils down to about 3.5 hours worth of time for 100 units of our production. And for a test production line of 100 units for a design that we have put numerous amount of time already into just designing it, we are more than willing to put another 3.5 hours worth of time. And with most startup companies in general, it is an early investment from its designers putting in time and work that they're not getting paid for, so that we can later hire someone else to do it as production and demand increases, which is why we had not currently included assembly times for something that is so minute in the grand scheme of design.
So I have my education in business, and I actually specialized in entrepreneurship. So I completely understand the new business concept. You do for a little bit, but if you're thinking, I'm going to make 100 of these and then I'm abandoning the project and moving on with life, okay. But if you're actually starting a business with this, then you really do need to look more into assembly costs.
Once demand reaches a point where we have to outsource, yes.
I believe our thought process was for this customer and this project in particular for a 100 unit production run. we would take it upon ourselves to do the manufacturing, just because to pay someone assembly labor would include a place for the assemblers to work, benefits and pay, which we did try calculating, and we found that it was outside of our price range for this particular customer. But with larger scale production, we would definitely have people to do this work for us who we would pay rather than doing it ourselves.
Well, and the thing is, if it's outside your cost limits, it's outside your cost limits. You know, you have two options: go back to the customer and see if they can get more money. That's always a possibility, you know, or like you said, you got to kind of wiggle and choose in other places where you're gonna, you know, I don't know what I'm talking about here. Acrylic material, maybe there's acrylic material or something. I don't know, you know. So I understand the concept of wanting to do it yourselves. I really do. But you've got to kind of start thinking, and in prototyping, fine. I expect you to do it yourselves. If you're outsourcing prototyping, what are you doing? So, you know, totally fine with that. But you really are going to want to start considering when you get into mass production, you know, you need to consider your labor costs. Yes, I understand it's 100, but what you're trying to present here is not necessarily what it would cost to do 100. You're trying to present what would it cost to do a lot of these into the future, you know? So again, just it's something to kind of consider that. And then I think you said that you were going to, did you say you were going to deliver it to the customer and then they were going to put the pieces together like a Lego, more or less?
The mounts would already be assembled. All the subsystems would be assembled, but
Okay.
the mounts would not be magnetically connected to the optics table because
Mhm.
our design is intended to be versatile and the users
Right.
are able to put the mounts wherever they want.
Okay, and I'm assuming this will come with some sort of simple instructions on how to do it. Someone like,
Yeah, some kind of manual assembly plan. We actually got one together for the final design report for tomorrow.
love it.
So
so the last thing you're going to want to kind of consider here is your delivery costs. You know, depending on how big your product is, how heavy it is, how delicate it is, you know, it could start really creeping up there to ship these things. So just kind of start, you know, thinking about, oh, well, if I've got to ship this one, you know, this one unit may cost me $20 to ship because, you know, whatever FedEx, you know, when you start massing producing these, oh, and, you know, if it's really delicate, then maybe you need to look at getting some foam, you know, to put in the inside to make sure the pieces don't bounce around. So that's, you know, again, that's getting real far into detail thinking about that, but just you will want to consider some type of delivery costs in here to get it to your customer so it doesn't break.
You are correct, and it is not something that we had considered. However, in our customer needs statement, it was not something we were supposed to include in our production run costs. It was assembly labor. And
did it specifically say don't include delivery costs?
It says includes materials, energy, fabrication labor, assembly labor, and profit.
Okay, and profit?
Profit, yes, ma'am.
Okay, so delivery is coming out of your profit.
But
So
it is
I understand. Look, I understand that, you know, I'm coming at you from a business frame of mind. I'm an investor, right? I totally understand this is not y'all's forte, right? But it's just something to think about going into the future. You know, hey, if we are going to do this, you know, we may need to look at this. We may need to look at that. I'm not saying what you have here is bad by any stretch of the imagination. Granted, I don't understand probably 2/3 of what you even had in your presentation. I love this slide because I can understand it. But, you know, just kind of things to think about, like, yes, this is how much it costs us to make it, but what happens when we need to get it elsewhere? What happens when we need to create more of these than we can because, you know, we're students or we have other jobs or stuff, you know, just kind of things to think about. But other than that, I really appreciate that y'all did actually go into, detail enough that it's down to cents and dimes. Lots of people are just like, oh, it's like $30. And then come to find out it's more like, $37.50, which is fine for the first one. But then when you're producing 100, 1,000, 2,000, that adds up. So I really appreciate that y'all went into detail here with the nickels and dimes, if you will, because that actually can nickel and dime you. I didn't even mean to make that pun, and I so did. So that's all I have for that. You all did a very good job.
Thank you.
Thank you.
Okay. So I think on that note, we're probably at a good time to wrap up because we're a good 30 minutes over where we were supposed to be. So we'll call it quits there. I just want to thank you guys for sharing your design and your presentation with us. You made it, right? We had some rough patches along the way with the customer need statement changing, and you guys kind of being orphaned in where you had put your initial focus, but we figured out, I think, a good path forward, and I think the end result was great. This was a really good presentation, and we had a really good technical discussion around it. So appreciate you guys rolling with the punches over the course of the semester and getting to the end the way you did. That was, I think, very professional of you to have approached it that way.
Thank you, Professor.
Yeah, thank you for
Thank you,
all
Professor.
that help,
Thank you.
for sure.
All because of you.
Great. Okay. Well, with that, you guys are the ones doing the recording. So I'll follow up with you guys on Teams to get the video so that we can archive it.